Another popular method in solving electrical circuits is called the nodal analysis. So in this video, we're going to describe how to use nodal analysis. So that will be one of our learning objectives. And the second is we will apply nodal analysis to solve network problems. Nodal analysis is heavy in the use of Kirchhoff's current law and Ohm's law. It does not use Kirchhoff's voltage law. So to explain how to use nodal technique, let's go back to the example that we used to explain mesh analysis. The first step in using nodal technique is to identify the nodes where at least three or more circuit elements are connected to that node. So that would be these nodes, this one and this one. So for example, this node here has the 2 ohms, 4 ohms, and 8 ohms connected, while this node here at the bottom, we have the 2 sources and the 8 ohms connected. The second step is to assign a node as your ground node, or what we call a zero potential node. So that would be the node with the highest number of elements connected. And from what we got is that this could either be this node or this node. So let me use the bottom node as the ground node. So when we label a node as the ground node, we usually attach a ground symbol that looks like this. And then for the remaining node, we just label it. So let's say this is the node A. Okay, so when we say a node is our ground node, that means that is the reference node. So associated with a ground node, we assign there the potential of that node. So that would be the 0 volts node. So what this means is that when a node is a ground node, the potential there is 0 volts. This is similar to a building. So for example, we have a building here and we specify this floor as our ground floor. So we can call this our 0 floor. And the next floors on top or below is referenced uh, based on this 0 floor or our ground floor. So for example, the next floor above, we call it the first floor, the second floor above, or the next floor would be our second floor, and so on. So that is really what we mean by a ground node. So it is a reference node where other nodes are referenced from it. The third step is to assume arbitrary currents in the elements or in the branch. So let's say in our 2 ohms, we have a current that is flowing in this direction. So let's say this is I sub x. Here, let's say we have here I sub y, and here, let's say we have I sub z. So these are purely arbitrary, meaning we could have used a different direction. So it's all up to you. We could have specified a current through the 5 volts and the 3 volts here. But the current through the 5 volts is also I sub x because of the 2 ohms and 5 ohms are in series. Also for the 3 volts, we could have specified the current, but uh, both 3 volts and 4 ohms are in series, so therefore there's no need to label or put the current through the 3 volts. And the next step is to identify the voltage potential for each node relative to the ground. So we said that the ground is a 0 volts node. The ground node is a 0 volts node, and we need to specify the uh, potential on each node relative to the 0 volts or relative to the ground. Well, for node A, what would be the potential? So we still don't know, and we just label it as vis-a-vis, so that is the potential there. We could also label this node here and here. So here, what will be the potential there? Take note that this point here, which is attached also to the 0 volts, so this point here should be 0 volts as well. And based on the positioning of the polarity of the 5 volts, this point here must be 5 volts higher compared to this point. So therefore, this point here must be 5 volts. And since this point is the same point as this point, this would be 5 volts. This point here is also attached to the ground, so therefore this must be 0 volts. And based on the position of the polarity of the 3 volts, this point must be negative 3 volts. So therefore, this point here is also negative 3 volts. Okay. So there you have it. I just made permanent the labels and the potentials that we have made on the last slide. So the fifth step is to write KCL equations for each of the nodes that we have identified where at least 3 or more elements are connected, with the exception of the ground node. So that would be the node A. So we need to create or write a KCL equation for that node. We don't write KCL equation for this node because there are only 2 elements connected. So proceeding to write the equation for node A, that equation would be this one. So current entering the node minus current leaving the nodes or the node should be equals to 0. So the next step is to replace the currents as a function of the voltage across the elements. So for example, I sub x can be replaced by its voltage across the 2 ohms divided by 2 ohms. So why is that so? Why is Ix equals 5 minus x, or 5 minus VA divided by 2? Okay. So let's say this is our 2 ohms there. So we said that the current here is I sub x. Um, since current is flowing through the 2 ohms, that means there is a voltage there. And that voltage is such that the plus is in here and the minus is in there. Now, what is the voltage across the 2 ohms? Now, take note that the potential here is 5 volts because this point is attached to the 5 volts, and this point here is V sub A. Now the voltage across an element is also the potential difference of its terminals. So the potential difference is 5 minus VA. So we write the first potential where the current enters. So the current enters at this point. So therefore we write 5 minus VA where the current exits the element. So that is 5 minus VA is the potential or the voltage across the 2 ohms. So by Ohm's law, voltage divided by the resistance must be the current flowing through the 2 ohms, and that should be equals to I sub x. So that's why we have here I sub x 5 minus VA divided by 2 ohms. So doing the same for 8 ohms, um, so the potential here minus the potential here. So the potential here is VA minus the potential here, which is 0, divided by 8. That should be I sub y. For I sub c, the potential here minus the potential there. So VA minus negative 3 divided by 4. So that should be I sub c. Now, take note that the currents I sub x, I sub y, and I sub z are actual currents flowing through the elements. These are not imaginary currents that we discussed a while ago in our previous videos for mesh analysis. And then we can replace these currents by the ones above, and that should give us this equation. So this is I sub x, I sub y, and I sub z. And then we can solve for v sub a. So with a little algebra, we can solve for v sub a, and that should give us 2 volts. And once we got the node voltages, we can solve for the branch currents. So the currents I sub x, I sub y, and I sub c. So solving them, that should give us these values here. And for the last step, we can now solve the required unknown. So I sub 1 is negative I sub x because I sub x is flowing in the opposite direction as I sub 1. So that should be negative I sub x. So we get I sub 1, negative 1.5, and V sub 3 is negative 8IY because the polarity based on the direction of I sub y should be plus here and negative there. But since V sub 3 is specified to be positive at the bottom, so therefore we write negative 8IY. And that should give us a negative 2 volts, which is the same result that we got in solving the problem using mesh analysis. Let's have our first example. So this is the same example that we did in mesh analysis, but here this time we really use nodal technique to solve for the current I that is flowing through the 1 ohm. So the first step again is to identify the nodes where 3 or more elements are connected. So these will be the nodes. So this one is node A, node B, node C, and we decide to make this node as our ground node. take note that uh, this whole thing here is node A, this is node B, node C, and here is our ground. Okay, so that is the scope of the nodes. The next step is to assign arbitrary currents. So let me just put them in here. So those are the arbitrary currents. So there are five of them. And then we label the nodes. We label the potential of the nodes with um, all the nodes, including those nodes that have two elements connected. So this again, as I've said, is V sub A, the potential of that node. This is V sub B, this is V sub C, and this thing here is 0 volts. Okay, this one here is 8 volts because this one is 0, and by the position of the polarity, this should be positive 8 volts. So we can now write the equations. So for node A, current entering minus current leaving must be equals to 0. So current entering this node is I sub 2 minus current leaving I sub 1 and I sub 3. So here is also I sub 3 there. And replacing the currents by the potentials or the voltage across the elements. So for 2 ohms, that will be V sub B minus V sub A divided by 2. For I sub 1, that would be VA. So we always write the first potential where the current enters, VA minus 0 divided by 4. I sub 3 here is VA minus VC divided by 3. So this is the one here. And simplifying, collecting like terms, that should give us this first equation. For node B, so current entering minus current leaving equals 0. Uh, so the current here through the 1 ohm is already assigned from the problem, so we use that current. So the current entering node B is I and I sub 4, so minus the leaving current, which is I sub 2, equals 0. So we replace um, I as the potential here, which is 8, minus the potential here, which is V sub B, divided by 1. So this is, it's here. For I sub 2, that would be the potential here minus the potential there divided by 2. So this is it. So it's actually the same here. Now I sub 4, what is the expression for I sub 4? Now take note that this is not a resistance. So therefore we cannot write an expression that replaces I sub 4 by the voltage. So we just leave I sub 4 there, and this gives us our equation 2 after simplifying this. For node C, this will be our KCL equation. So take note that the current here is also I sub 3. And replacing the currents by the potentials. So for I sub 3, that should be this one. So the same one that we got earlier. For I sub 5, that would be the potential here, which is 0 minus V sub C divided by 5. And I sub 4, again, we cannot express it as the potentials because this is not a resistance. So we'll just leave it as that. So this will be our third equation. Now, take note that we could also relate. Uh, so we have three equations, but uh, we have four unknowns because of the presence of I sub 4. We need one more equation to solve the problem. So take note that we could relate V sub B and V sub C using the 6 volts here. So take note that due to the position of the polarity of the 6 volts, this point here must be 6 volt higher compared to this one. But the potential difference across the terminals of the 6 volts can also be expressed in terms of the potentials V sub B and V sub C. And that should be V sub B minus V sub C equals 6 watts. Okay, so that would actually be that one. So that would be our equation 4. So we can solve the problem now because we have four equations for nodes. Now we can start by eliminating I sub 4, and we could do that by adding equations 2 and 3. So if we do that, we get this equation. And collecting all the equations, uh, 1, 5, and 4, we now have a three equation, three unknown problem, and we can solve for the potential voltages. So that would give us these results. And lastly, we can now solve for the current I, which is really just this potential here, 8 volts minus V sub B, which you already know, divided by 1 ohm, then that should give us this answer, which is the same answer that we got in using mesh analysis. Um, so let's have this example. I think this is the last example. Oh, this is second to the last example. So here we have a current source. So we just follow the steps again in using Nodal technique. So first step is to identify the nodes and define or assign a ground node. And by our rules, this node should become our ground node. And so we label the remaining node as A, B here, A here, B here. And we express or we assign potentials on each of the nodes. So that should be the nodes or the potentials on the nodes. So we don't know the potential at node B, so we'll just label it at V sub B. In A, we label it V sub A. Now we can label uh, this node. We can assign potential there by way of V sub B. So based on the positioning of the polarity for the 20 ohms, this node here should be 20 volts lower than this node. But since this node is V sub B, that means this node here should be V sub B minus 20. This node here is 40 volts higher than this node, but since this node is V sub B, that means that this node should be V sub B plus 40 volts. Now we could use this, we could label this node, or we could assign this node as our ground node, and that should give us the potentials on this point as simply as 40 volts, and this one as negative 20 volts here. Here it's still the same V sub A, and here it's V sub B, which looks uh, simpler compared to the previous assignment of the ground node. So we'll just use this configuration. So we can now write our equations. So we have the assigned arbitrary currents there. So I sub 1 is here, I sub 2, I sub 3, and I sub 4. Take note that we didn't assign arbitrary current here because we already know the current that flows in these lines, and that is 5 amperes. So we can now write KCL equation for node A. We have this equation. So current entering is I sub 1 minus current leaving. So here, the current here is actually in this direction, is 5 volts or 5 amperes. So that's why it is included in this equation. And then I sub 1 can be replaced by 40 minus VA divided by 1. So this is I sub 1 here. And I sub 2 is VA minus VB divided by 2. So here, and we transfer the 5 on the other side of the equation. And simplifying this one, we should get this equation 1. Now for node B, we could also write KCL, and this is the KCL equation, and replacing the currents by the node voltages or node potential voltages, we get this, and simplifying, we get equation 2. And since we only have two node voltages or node potential voltages, we can now solve the problem. So that should give us V sub A as 30 and V sub B as 20 volts. And V naught, which is the required unknown, must be the potential here, which is V sub B minus the potential there. So that is V sub naught. Okay. Okay, let's go through our last example. So in this last example, we're required to get V sub x and I sub 1. So let's proceed in the solution. So I already assigned the ground node here, and also assigned the remaining nodes, including the potentials for the nodes, and also assign arbitrary currents through each of the elements. So here we didn't assign a branch current because it's already there. We already have the current there. So take note that this whole thing here is a ground node. This whole thing here is V sub A, and this is V sub B. So let's proceed to write the KCL equations. For node A, we'll have current entering as 15 minus current leaving. So 15 minus I sub 1 minus I sub 2. After simplification, that should give us this equation. And replacing the currents by the potentials, that should give us this equation. And this equation number 1. For node B, so that would be the current entering minus current leaving. So current entering is this current here, 3I1. So take note that is a current entering quantity plus I sub 2 minus I sub 3 equals 0. So we can replace I sub 2 by VA minus VB divided by 1. So this is I sub 2 here. Now I sub 1. So take note this is a dependent current source whose value depends on this current. And we could replace I sub 1 by VA minus 0. So this point here is 0 volts divided by 2. So that should give us VA over 2. And I sub 3 is VB minus 0 divided by 3. And that should be this one. Simplifying, that should give us this equation here. So solving for the well, we did not solve for the values of the node voltages VA and VB, but after solving those voltages, we could solve Vx by this equation and I sub 1 by that equation. So that wraps up our video for the methods of analysis for resistive circuits. So what we did is to introduce two popular methods in solving resistive networks. So those are the mesh analysis and the nodal analysis. So in the mesh analysis, we use their Kirchhoff's voltage law repeatedly. We solve for the loop currents there first, and then after that we can solve for the voltages. In the nodal analysis, what we did is we solved first for the nodal voltages, and after that we solve for the branch currents. So for our next video, we will be dealing with network theorems. So these are theorems that will further help us in our network analysis efforts.